Every single object you have ever touched, every surface your fingers have traced, every wall you have leaned against, and every breath of air that has moved through your lungs has felt completely solid and undeniably real. The world pushes back. Matter resists. Things fall, collide, occupy space, and persist through time. The experience of physical reality is so total and so immediate that questioning it feels almost absurd. And yet, for more than a century, physics has been accumulating evidence that the nature of reality is far stranger than it appears. Not strange in a poetic or philosophical sense. Strange in a precise, mathematically verified, experimentally confirmed sense. The discoveries sit not in philosophy journals, but in the most rigorous experimental physics literature in existence. In 2022, the Nobel Prize in Physics was awarded for a set of experiments that proved something remarkable. The universe, at the most fundamental level, does not have definite properties until something interacts with it. Particles do not possess fixed states while no one is looking. Objects do not have certain measurable values sitting quietly in space waiting to be discovered. Instead, the act of measurement itself appears to bring those properties into existence. This is not a poetic metaphor. It is not a philosophical position. It is the conclusion reached by decades of increasingly precise laboratory experiments, now honored by the highest award in science. Understanding what that actually means, what it implies about the nature of matter, space, consciousness, and existence itself, is one of the most profound journeys in contemporary science. The story begins not with a lab result, but with a very old question. What is the relationship between the world as it appears and the world as it actually is? 2,500 years ago, a pre-Socratic Greek thinker named Parmenides was already wrestling with this problem in a surprisingly rigorous way. Parmenides argued that the world we experience through our senses is fundamentally an illusion. What we see, hear, and feel is not the true nature of things. The real nature of the world, he insisted, is only accessible through reason. Furthermore, this underlying reality is unchanging, unified, and without beginning or end. His argument was built on a deceptively simple foundation. He asked his contemporaries to consider the concept of nothing. He pointed out that the concept of nothingness is inherently irrational. You cannot coherently think about something that does not exist, because the moment you think about it, it becomes something your mind is engaged with. From this, he concluded that truly empty space cannot exist. And if there is no empty space, there is nowhere for objects to move into. Therefore, motion itself must be impossible. From there, he proceeded to refute the ideas of change, difference, and ending, concluding that all of these are features of the illusory world of appearances, not the underlying reality. The world we interact with, in his view, is not the real world. It is a story our senses tell us, a convincing fiction. Parmenides is often dismissed as a historical curiosity, a thinker whose conclusions were too radical and whose arguments were too abstract to have any scientific bearing. But the strange thing is that modern physics has arrived at a remarkably similar destination through a completely different route. Not through philosophical reasoning about nothingness, but through carefully designed laboratory experiments measuring the behavior of individual particles. Physics begins its version of this story in the early 20th century. Scientists at the time were pursuing a very concrete goal. They wanted to understand how atoms work. By the 1920s, a series of experiments had established that atoms consist of a small, dense, positively charged nucleus surrounded by a cloud of negatively charged electrons. Niels Bohr developed a model in which these electrons orbit the nucleus in specific allowed paths, each associated with a particular energy level. The model worked remarkably well for predicting the light emitted and absorbed by hydrogen atoms. But it raised immediate questions. Why do electrons only occupy certain orbits? What determines those orbits? What is actually happening at the level of individual particles? The answers that emerged over the following decade were completely unexpected. Electrons, it turned out, do not simply behave like tiny charged balls moving through space. They also behave like waves. Depending on the experimental setup, the same electron could display either particle-like behavior, appearing at a definite location at a definite time, or wave-like behavior, spreading out across space and passing through multiple openings simultaneously. This was called wave-particle duality, And it immediately raised a disturbing question. What is an electron really? Is it a particle or a wave? The honest answer, as experiments continued to confirm, is that it is neither in any familiar sense. It is something that behaves like a particle under certain conditions and like a wave under others. The electron does not fit into any category drawn from everyday experience. The formalism that emerged from this period, quantum mechanics, handled the situation by describing particles through what is called a wave function. The wave function is a mathematical object that encodes the probability of finding a particle at any given location or in any given state when a measurement is made. Between measurements, the wave function evolves according to perfectly deterministic equations. It spreads, combines with other wave functions, interferes with itself. But when a measurement is performed, the wave function collapses to a definite outcome. Before the measurement, the particle exists in a superposition of multiple possible states simultaneously. After the measurement, it has a single definite state. This process is called wave function collapse, and it sits at the heart of the most debated question in physics. What is actually happening between measurements? There are several competing interpretations of this process, and physicists have argued about them for nearly a century. But what is not debated is the experimental record itself. Quantum mechanics makes predictions of extraordinary precision, and those predictions have been confirmed to a degree no other scientific theory has matched. The fine structure constant, which governs the strength of electromagnetic interactions, has been measured experimentally and calculated from quantum theory to agree to more than 10 decimal places. The theory works. The mystery is what it means. One of the deepest mysteries concerns local realism, a set of intuitions most people carry about how the physical world works. Local realism consists of two distinct assumptions. The first is realism, the idea that objects have definite properties that exist independently of whether anyone is observing or measuring them. An apple sitting on a table has a definite color and mass regardless of whether anyone is looking at it. The second is locality, the idea that objects can only be influenced by things in their immediate surroundings. Nothing can act on an object from a distance instantaneously. Any influence must travel through space and is therefore limited by the speed of light. These two assumptions seem so obviously true that questioning them feels like questioning whether numbers add up. And yet, in 1964, a physicist named John Bell proved mathematically that these two assumptions together produce specific constraints on the outcomes of certain experiments. Bell showed that if local realism is correct, the correlations between measurements on separated particles must obey a set of mathematical inequalities, now known as Bell inequalities. If experiments ever find correlations that violate those inequalities, it means local realism is wrong. At least one of the two assumptions must be false. The experiments were performed beginning in 1972 by John Clauser and were then extended and refined over subsequent decades by Elaine Aspect and Anton Zeilinger. The results were clear. The Bell inequalities were violated. The correlations observed between particles exceeded what local realism permits. In 2022, Clauser, Aspect, and Zeilinger received the Nobel Prize in Physics for this body of work. The conclusion, stated as plainly as possible, is that the local realist view of the universe is almost certainly false. The universe does not work the way our intuitions tell us it should. What exactly does this mean? The violation of Bell inequalities implies that particles separated by arbitrary distances can be correlated in ways that cannot be explained by any information or signal traveling between them at or below the speed of light. This phenomenon is called quantum entanglement. Two particles become entangled when they interact or are created together in a specific way. After that, measurements performed on one particle will correlate with measurements performed on the other, regardless of the distance between them. The correlation is not due to any hidden properties the particles carried with them from their point of creation. Bell's theorem and the experiments that followed it ruled out that explanation. The correlations arise from something else, something that has no equivalent in classical physics. It is important to be precise here about what quantum entanglement does and does not imply. Entanglement does not allow faster-than-light communication. The measurement outcomes on each individual particle appear random, and it is only when the two sets of results are compared that the correlation becomes visible. Since comparing them requires transmitting information through conventional channels limited by the speed of light, no signal travels faster than light. But the correlations themselves are real and cannot be explained within any locally realistic framework. The universe simply does not operate according to the rules we thought applied. The experiments also confirmed a second troubling feature of quantum mechanics. Particles do not appear to have definite values for certain properties before those properties are measured. In the entanglement experiments, particles are given a property called spin. Spin can point in different directions, and experimenters can choose which direction to measure. Before the measurement, the particle is not in a definite spin state. The spin exists in a superposition. When the measurement is made, the outcome is random, with probabilities determined by the wave function. When two entangled particles are measured, their outcomes are correlated in specific ways that depend on the relative orientation of the measurement devices. Even when the measurement choices are made so late and so far apart that no signal could possibly travel between the particles in time to coordinate the outcomes. The implication is striking. The universe, at the fundamental level, does not consist of objects with fixed properties sitting quietly in space. It consists of something that takes on definite properties only through interaction, through the act of measurement or observation. Before interaction, properties are not simply unknown. They are, in a real and experimentally supported sense, not yet determined. The universe is, at its most basic level, radically different from the solid, definite, locally influenced world of everyday experience. This realization connects to something neuroscience has been establishing from a completely different direction. The world that you consciously experience is not a direct perception of an external reality. It is a construction built by your brain. This distinction matters enormously, and it is not a philosophical caveat or a minor technical qualification. It is a central fact about how perception works, supported by a substantial body of experimental evidence. Your eyes collect light. Your ears collect pressure waves in air. Your skin responds to temperature, pressure, and chemical signals. None of these sensory organs deliver the world directly to your consciousness. Instead, they convert physical signals into electrical impulses that travel along nerve fibers to the brain. The brain then performs an elaborate reconstruction, using those signals as input data to generate an internal model of the environment. The model is what you experience as reality. This reconstruction is not a passive recording. It is an active inference process. The brain is constantly making predictions about what the sensory input means, drawing on prior experience, pattern recognition, and contextual expectation. When the sensory data is ambiguous, the brain resolves the ambiguity by choosing the interpretation most consistent with its prior model. This is why optical illusions work so reliably. An illusion is not a failure of the visual system. It is the visual system doing exactly what it is designed to do, resolving ambiguous information in the most probable way, and in these specially constructed cases, getting a different answer than the physical reality would suggest. Consider what happens when the pattern of light reaching your eyes creates ambiguous cues about motion. The brain reads those cues through a framework built up from a lifetime of experience with how moving objects produce changes in illumination. In a carefully constructed image, the brain concludes that an object is moving diagonally when it is in fact moving in a straight vertical line. Tracing the motion with a finger reveals the discrepancy. The finger, which has direct physical contact with the screen, reveals one reality. The visual system, processing patterns of light, constructs another. The brain's construction wins in terms of what you experience consciously, but the finger reveals the underlying truth. This is not an edge case. It is the normal operating mode of perception. Every piece of visual information you experience has been processed, interpreted, and reconstructed by neural circuits before it reaches consciousness. The same is true of sound, touch, smell, and taste. The unified, continuous, fully saturated experience of reality that feels so immediate and undeniable is an output, a computational product of an organ that never gives you direct access to the physical world. The neuroscientist Anil Seth has described this as controlled hallucination. Hallucination is not the right word in everyday usage, because we reserve that word for experiences that are wildly false. But the underlying process is similar. The brain generates a model. The model is informed by sensory data, but the model is not the same thing as the data. When sensory information is rich and consistent, The model closely tracks the external world. When information is sparse or misleading, the model fills in gaps using prior knowledge and expectation. The gap filling is usually invisible to conscious experience. This has deep implications. If the experience of reality is always a construction rather than a direct reading, then the question of what reality is like, independent of any observer, becomes genuinely difficult. You cannot simply step outside your perception to check whether your experience matches the underlying world. You have only the model. Every check you perform, every experiment you run, every measurement you make is itself processed through the same constructive perceptual system. You are always, in a sense, inside the model. This is where the history of consciousness studies becomes relevant. For most of the history of Western philosophy, consciousness was treated as a thing clearly present in humans and clearly absent in rocks, and the boundary between those extremes was drawn wherever convenient. John Locke, writing in 1690, defined consciousness as the perception of what passes in a man's own mind. This definition placed consciousness squarely inside the skull, as a kind of internal observer watching the stream of thoughts and perceptions. The definition was useful, but raised an immediate question. How does the perception of mental states arise from physical processes in the brain? This question, now called the hard problem of consciousness, is still unsolved. Neuroscience has made enormous progress in understanding which brain regions are active during different mental states, how neurons communicate, how learning and memory work, and how damage to specific areas produces specific changes in behavior. But explaining why any of this physical activity should be accompanied by subjective experience, why there is something it feels like to see red or feel pain, rather than simply having those signals processed without any accompanying inner experience, remains genuinely open. The physical processes can be described completely. The connection between those processes and the fact of subjective experience has not been bridged. William James, writing in 1890 in his foundational work on psychology, described consciousness as a stream rather than a series of discrete states. He identified several features of this stream that continue to influence thinking about consciousness. Thought is continuous, with no sharp boundaries between one moment and the next. It is personal, always occurring from a particular point of view. It is constantly changing, never returning to exactly the same state. And it is selective, attending to some aspects of the available information and ignoring others. The stream metaphor captured something important about the temporal character of consciousness, its flowing dynamic quality that resists reduction to a collection of snapshots. Later, theories tried to ground consciousness more firmly in physical processes. One influential framework, integrated information theory, proposes that consciousness is a property of any system that integrates information in a specific way. The degree of consciousness, measured by a quantity called phi, corresponds to how much information a system generates as a whole, beyond what its parts generate individually. On this view, consciousness is not confined to biological brains. It is, in principle, a property of any sufficiently integrated information processing system. The brain has particularly high integrated information, which is why human consciousness is particularly rich. But a simple thermostat might have a tiny but non-zero amount. The theory makes a specific mathematical claim that can, at least in principle, be tested. Whether integrated information theory is correct remains debated, but it represents a serious scientific attempt to say something precise about what consciousness is and why it exists. The fact that natural laws governing particle motion and energy transfer do not obviously require or predict the existence of subjective experience is genuinely puzzling. Evolution by natural selection is a powerful force, but it selects for behaviors, not experiences. A creature could in principle respond to stimuli, learn from experience, and survive and reproduce without any accompanying inner life. The existence of subjective experience seems, on the surface, to require explanation. This gap between the physical and the experiential connects to one of the most provocative ideas in contemporary thinking about reality, the possibility that our universe is itself a kind of information processing system. The connection between information and physical reality has been developing for decades, beginning with work in thermodynamics and accelerating through discoveries in quantum physics and cosmology. The physicist John Archibald Wheeler one of the major figures in 20th century physics, developed a phrase late in his career that captured a radical possibility: it from bit. The phrase meant that everything in the physical world, every particle, every field, every interaction, derives its existence from information. Not from fundamental matter or energy in the traditional sense, but from the yes or no binary distinctions that constitute information. Particles have properties because something somewhere registered a binary outcome. Reality is, in this view, built not from stuff, but from data. This idea would have seemed impossibly abstract if it had not been given unexpected support from a completely different direction. In the 1990s, research into the thermodynamics of black holes led to a stunning theoretical result. A black hole has entropy, a measure of the information stored in the matter that formed it. That entropy, calculated by Stephen Hawking and Jacob Bekenstein, is proportional not to the volume of the black hole, but to the area of its event horizon, its surface boundary. This is deeply counterintuitive. If you imagine filling a region of space with matter, the amount of information you might expect it to contain should scale with its volume, with the three-dimensional space inside. The fact that black hole entropy scales with area instead suggests something extraordinary. The theoretical physicist Gerard Hooft formalized this into what is now called the holographic principle. The holographic principle states that all the information needed to describe the physical content of a three-dimensional region of space can be encoded on its two-dimensional boundary surface. This is analogous to a hologram, a two-dimensional surface that contains enough information to reconstruct a full three-dimensional image. In the holographic picture, the three-dimensional world you move through might be, in a deep mathematical sense, a projection from a two-dimensional surface containing all the underlying information. This is not merely speculative. The holographic principle has been given precise mathematical realization in a framework called the anti-de Sitter conformal field theory correspondence, developed primarily by Juan Maldacena in 1997. This correspondence establishes a precise mathematical equivalence between a specific type of gravitational theory in a particular space and a quantum field theory living on the boundary of that space, with one fewer dimension. The two theories are mathematically dual descriptions of the same physical situation. Everything that happens in the bulk of the space, including all the gravitational physics, is completely encoded in the boundary theory. The interior is, in a rigorous sense, a projection from the boundary. The deeper implication of the holographic principle, if it holds generally, is that the seemingly solid three-dimensional universe we inhabit may not be fundamental. The world of volume and depth, of objects separated by distances and interacting locally, may be an emergent description that arises from something more fundamental happening on a lower dimensional surface. Space itself may not be a primary ingredient of reality. It may be something that appears when a more fundamental structure is viewed from a particular perspective, the way a hologram appears three-dimensional when illuminated correctly, even though the surface encoding it is flat. Recent research in quantum gravity has developed this idea further through the concept of entanglement and the geometry of space. One striking proposal, developed over the past 2 decades, holds that entanglement between quantum states is what gives rise to the geometry of space-time in the first place. In this picture, 2 regions of space are connected to each other precisely because the quantum states describing them are entangled. Remove the entanglement, and the connection between the regions dissolves. Space, as a geometric structure, is not primitive. It emerges from the pattern of quantum correlations in a more fundamental description. This idea, sometimes summarized in the phrase ER equals EPR, connects 2 seemingly unrelated phenomena. ER refers to the Einstein-Rosen bridge, the theoretical connection between 2 black holes predicted by general relativity, and also called a wormhole. EPR refers to the Einstein-Podolsky-Rosen paper, the famous 1935 paper that first clearly articulated the phenomenon of quantum entanglement, which Einstein described as spooky action at a distance. The proposal is that an Einstein-Rosen bridge between 2 black holes is physically equivalent to the quantum entanglement between them. Spatial connection and quantum correlation may be 2 descriptions of the same underlying phenomenon. Space-time geometry and quantum information may be aspects of a single deeper structure. The implications extend to matter itself. Recent theoretical work suggests that not only the geometry of space-time, but also the matter fields that live in it may emerge from entanglement structure. Dark matter and dark energy, the mysterious components that make up roughly 95% of the energy content of the universe, according to cosmological measurements, may in this framework be understood as features of the entanglement structure of the underlying quantum description, rather than as separate entities requiring separate explanations. These theoretical developments are not experimentally confirmed in their full generality. They are active research directions pursued by physicists at major research institutions worldwide. But they represent serious scientific proposals grounded in well-established formalisms, and they have produced specific mathematical results that connect previously separate fields. The picture they collectively suggest is one in which information, not matter or energy in the classical sense, is the most fundamental ingredient of physical reality. One of the more striking ways to approach the nature of information in physics is through the question of what happens to information when matter falls into a black hole. A black hole, in classical general relativity, is a region of space from which nothing, including light, can escape. If matter falls in, it is gone. The information it carried, the specific arrangement of particles and fields that constituted that matter, is apparently destroyed. But quantum mechanics insists that information cannot be destroyed. Physical processes are reversible at the fundamental level. If information goes in, information must somehow come out. Stephen Hawking showed in 1974 that black holes do emit radiation due to quantum effects near the event horizon. This Hawking radiation slowly carries energy away from the black hole, causing it to shrink over astronomically long timescales. But in Hawking's original calculation, this radiation was completely random, carrying no information about what fell in. The information appeared to be truly lost. This became known as the black hole information paradox, and it has been one of the most productive puzzles in theoretical physics for the past 50 years. Recent work, including contributions connected to the holographic principle and entanglement, has increasingly pointed toward information being preserved. The radiation emitted by a black hole over its entire lifetime appears to be subtly correlated in ways that encode the information about whatever fell in. The information is not destroyed. It is scrambled, mixed into correlations across many emitted particles in a way that makes it practically impossible to recover, but not fundamentally erased. This resolution, if correct, is consistent with the view that information is genuinely fundamental, that the laws of physics, at the deepest level, conserve the total information content of the universe even as they shuffle and redistribute it. The idea that reality might be made of information, rather than of matter and energy as traditionally conceived, connects naturally to a more radical possibility that has gained serious attention in the past 2 decades. That the universe we inhabit is not just described by information, but is itself a kind of computational process. This is the simulation hypothesis, a proposal that has attracted both careful philosophical analysis and heated dismissal. The argument was put on rigorous footing by the philosopher Nick Bostrom in a paper published in 2003. Bostrom identified what he called a trilemma. He argued that at least one of 3 propositions must be true. Either virtually all technologically advanced civilizations go extinct before reaching the computational capability to run detailed simulations of minds, or virtually all technologically advanced civilizations that do reach that capability choose not to run such simulations, or we are almost certainly living in a simulated reality right now. The logic runs as follows. If future civilizations can run vast numbers of detailed simulations of consciousness, and if they choose to do so, then the number of simulated conscious minds in existence would vastly outnumber the biological ones. In a universe containing millions of times more simulated minds than biological ones, a randomly chosen conscious observer is overwhelmingly more likely to be simulated than biological. The argument does not prove that we are in a simulation. It identifies a trilemma, and which prong of the trilemma we occupy is unknown. But it makes the simulation hypothesis a legitimate object of scientific and philosophical inquiry rather than pure speculation. Whether a simulated universe is physically distinguishable from a non-simulated one, and whether any experiment could in principle detect signs of simulation, are genuine research questions. Some physicists have proposed specific signatures that might indicate a simulated universe. If the simulation runs on a discrete computational substrate, space and energy might be quantized at a fundamental level rather than truly continuous. Interestingly, quantum mechanics already describes energy as quantized, and there are theoretical reasons to think space itself might be discrete at the Planck length, roughly 1.6 times 10 to the negative 35 meters, a scale so small it is 20 powers of 10 smaller than an atomic nucleus. Whether this quantization is a genuine feature of continuous nature or a hint of an underlying computational grid is not currently distinguishable. But the question is being taken seriously. Another proposed signature involves the distribution of the highest energy cosmic rays, the most energetic particles observed arriving at Earth from distant sources. A computational universe running on a finite lattice might impose direction-dependent constraints on particle energies at the highest scales, since a spatial lattice has preferred directions corresponding to its grid axes. Searches for such directional dependence in the highest energy cosmic ray data have been proposed as potential tests. So far, no conclusive signal has been found, but the searches continue and the observational data improves. The philosopher David Chalmers, known primarily for coining the term hard problem of consciousness, has argued that even if we are in a simulation, this does not make reality less real in any important sense. The simulation would be physical reality from our perspective, governed by consistent laws, providing stable grounds for knowledge and action. Whether there is a higher level beyond the simulation is, in this view, a further question that does not undermine the reality of our experience. In some sense, asking whether reality is real is asking what we mean by real. If we mean reliably consistent and accessible to shared investigation, then the simulated universe qualifies. If we mean something more, we need to specify what that something more is before the question becomes answerable. The connection between consciousness and reality takes on additional depth in light of the quantum measurement problem. Different interpretations of quantum mechanics make different claims about the role of consciousness in the measurement process. The Copenhagen interpretation, developed primarily by Niels Bohr and Werner Heisenberg, holds that quantum mechanics does not describe what happens between measurements, but only predicts measurement outcomes. The wave function is a calculational tool, not a description of physical reality independent of observers. On this view, asking what an electron is doing when no one is measuring it is a meaningless question. The concept of objective physical states existing independently of observation is simply not part of the theory. The many worlds interpretation, proposed by Hugh Everett in 1957, takes a different approach. It holds that the wave function always evolves deterministically and never collapses. When a measurement is made, all possible outcomes occur, but in different branches of a continuously branching reality. Consciousness does not collapse the wave function. Instead, consciousness branches along with everything else. From inside any given branch, the measurement appears to have a single definite outcome, because the observer and the measuring apparatus are all part of the same branch. But all outcomes are equally real from a global perspective. Relational quantum mechanics, proposed by Carlo Rovelli in 1996, holds that quantum states are not absolute properties of systems, but are always defined relative to some other system. There is no single global wave function encoding the state of everything. Instead, different observers have different, potentially incompatible quantum descriptions of the same events. What counts as a measurement outcome depends on who is asking. Reality, on this view, is not a single fixed structure, but a network of relationships with different observers, each having access to a partial and perspective-dependent description. Each of these interpretations is consistent with all known experimental results. No experiment to date has distinguished between them. They make identical predictions for every observable quantity. What they differ on is the deeper ontological story, what is actually happening in the world beyond the predictions. This situation is unusual in science. Normally, competing theories can be tested against each other. Here, the theories agree on everything you can measure and disagree only about what is real when you are not measuring. The question of which interpretation is correct may be genuinely undecidable, at least within the framework of physics as currently practiced. The question of what consciousness is and where it comes from remains one of the deepest open problems. The integrated information theory mentioned earlier is one approach. Another is the global workspace theory, developed by Bernard Bars and later extended by Stanislas Dehaene and others. Global workspace theory proposes that conscious experience corresponds to information being broadcast widely across the brain, made available to many different cognitive processes simultaneously. Information that is processed locally, used by a specific subsystem without being broadcast, remains unconscious. Consciousness, on this view, is what it feels like to be at the hub of a globally shared information system. These theories are not yet at the stage where they make predictions precise enough to be fully tested, but both have generated research programs that have produced real empirical results. We know more than we did about which patterns of brain activity correlate with conscious experience and which do not. We know more about how anesthesia works at the neural level and why certain brain states produce loss of consciousness while others do not. The understanding is incomplete, but it is growing. What the science collectively suggests, drawing together quantum mechanics, neuroscience, information theory, and theoretical physics, is a picture of reality substantially different from the one common sense provides. The world you experience is a construction built by your brain from incomplete and ambiguous sensory data. The underlying physical world does not consist of objects with definite properties existing independently of observation. Properties come into being through interaction. The geometry of space-time may emerge from patterns of quantum entanglement. Information may be the most fundamental ingredient of physical reality rather than matter or energy in the classical sense. And whether the entire structure of physics operates more like a computation than like machinery running on continuous substance remains a genuine open question. None of this means that everyday reality is untrustworthy for practical purposes. The apple falling from the tree follows a reliable trajectory. Engineering calculations produce bridges that stand. Medicine developed within this framework saves lives. The constructed model your brain generates is extraordinarily good at tracking the features of the physical world that matter for survival, prediction, and manipulation. The discrepancy between the model and the underlying reality is only detectable at extremes, in quantum experiments, in the vicinity of black holes, in careful studies of perception and illusion. For everyday scales and everyday purposes, the model and the reality are aligned closely enough that the distinction is invisible. But science is not only about practical purposes. It is also about understanding what is actually true. And the most rigorous, most carefully tested science we have suggests that the actual truth is considerably stranger than the everyday model. Particles lack definite properties until measured. This is not speculation. It is a conclusion forced by decades of experiments that won a Nobel Prize. Space may be not a container that exists independently, but something that emerges from quantum relationships. This is a serious theoretical proposal with mathematical backing, not a metaphor. The experience of reality you have right now is a construction produced by neural computation, not a transparent window onto the physical world. This is supported by a century of neuroscience and experimental psychology. What remains unknown is not small. We do not know why there is something rather than nothing. We do not know why the laws of physics have the particular form they do, why certain constants take the specific values they do, or why those values fall in the narrow range compatible with the existence of complex matter and eventually conscious observers. We do not know which interpretation of quantum mechanics, if any of the existing ones, correctly describes the underlying reality. We do not know whether the holographic principle applies to our actual universe in any rigorous way or only to specific theoretical models. We do not know whether consciousness is a fundamental feature of reality, an emergent property of sufficiently complex information processing, or something else entirely. We do not know whether the universe had a beginning, whether it is the only universe, or whether the concept of a beginning even applies to the totality of existence. These are not gaps waiting to be filled by already known methods. Several of them require conceptual breakthroughs that have not yet occurred, frameworks that do not yet exist, ways of thinking about space, time, information, and experience that nobody has yet invented. The history of physics is a history of exactly this kind of conceptual revolution. The invention of calculus changed what questions could be asked about motion. The development of non-Euclidean geometry changed what spaces could be considered. The formulation of quantum mechanics changed what could be said about the definiteness of physical properties. The next revolution, whatever it turns out to be, will almost certainly be similarly dramatic. What the current situation in science suggests, across multiple independent fields, is that the relationship between mind and world, between the observer and the observed, between information and physical reality, is far more intricate than either traditional science or traditional philosophy assumed. The questions that feel most ancient, what is real? What can we know? What is the nature of experience? Turn out to be precisely the questions that modern physics and neuroscience are most directly confronting. Not through speculation or abstraction, but through experiments that probe particles at femtoscale distances, through theoretical frameworks that reveal unexpected connections between black holes and information, through careful studies of how perception constructs the experienced world from neural signals. The universe we live in is one in which a particle can lack a definite spin until it is measured, in which two particles separated by billions of light years can be correlated in ways that cannot be explained by any local signal, in which the surface of a black hole can encode all the information describing its interior, and in which the three-dimensional experience of solid objects and continuous space may be an emergent description arising from something more fundamental. This is not the universe common sense predicts. It is the universe that careful measurement and rigorous theory have uncovered. Understanding it more fully is one of the central tasks of science in the coming decades. The researchers working on these questions are not offering easy answers or dramatic revelations. They are building mathematical frameworks, designing experiments, and following the logic of evidence wherever it leads. The destination remains unclear, but the direction is unmistakable. Reality, whatever it ultimately is something that will require new ways of thinking to fully comprehend. The questions are old. The tools for pursuing them have never been more powerful. And the discoveries accumulated so far suggest that what lies ahead is not a confirmation of old intuitions, but a continued and deepening transformation of what we thought we understood about the nature of existence. To understand why physicists take the non-reality of local realism so seriously, it helps to follow the logic of Bell's theorem in a more concrete way. Imagine two researchers, each working in a separate laboratory far apart. Before the experiment begins, a source in the middle sends one particle to each researcher. The two particles are entangled. Each researcher has a device that can measure a property of the particle called spin, and each can choose the orientation of their measuring device independently, essentially choosing which direction in space they want to measure spin along. The key constraint is that neither researcher knows what the other has chosen until after the measurements are recorded. For each measurement, the outcome is binary. Spin either aligns with the chosen direction or opposes it. The researchers record strings of outcomes. When they compare results afterward, they compute how often their outcomes agree or disagree. Bell showed mathematically that if the particles carry predetermined values for spin along all possible directions, values that were fixed when the particles left the source and carried with them through space, then the rate of agreement between the two researchers' measurements, computed over many runs with different randomly chosen orientations, cannot exceed a certain level. This is the Bell inequality. It is a mathematical consequence of assuming that the particles have definite properties before being measured. The experiments found agreement rates that exceeded this limit, not by a small amount that might be explained by experimental error, by an amount large enough to be conclusive. The particles do not carry predetermined spin values. The outcomes are genuinely undetermined before the measurements take place. And yet, when both researchers choose the same measurement direction, they always get perfectly correlated outcomes, one spin up and one spin down. This perfect correlation without any hidden predetermined values is the heart of what makes quantum entanglement so strange. The loopholes in these experiments were systematically closed over decades. Early experiments could be objected to on technical grounds. Maybe the particles actually carry hidden values, but the detectors are not perfectly efficient, so some results are selectively missed in a way that creates a false appearance of violation. This is the detection loophole. Or maybe the choice of measurement direction is not truly independent of the particle states, because all choices in the laboratory are made by physical systems that might be correlated with the particle source through unknown influences. This is the locality loophole. The Nobel Prize-winning work of Clauser, Aspect, and Zeilinger progressively addressed these loopholes with increasingly refined experiments. By 2015, experiments in Delft and elsewhere closed both major loopholes simultaneously in a single experiment. The violation of Bell inequalities is real and cannot be explained away. This means nature is non-local in a precise technical sense. The correlations between distant particles cannot be explained by any information or influence that was present at their creation point and traveled with them. Something about the overall configuration of the experiment, the setting of both measuring devices, and the two outcomes, is more correlated than any local realistic theory permits. This is a fact about the physical world. It is not an interpretation or a philosophical position. It is what the data show. The question of what this non-locality means for our picture of physical reality is where interpretation enters. The non-locality demonstrated by Bell experiments is not the kind that allows faster-than-light signaling, but it does mean that the universe cannot be fully described by a picture in which objects have definite properties and influences travel locally. Some essential feature of physical reality is distributed in a way that is not captured by the classical picture of separate objects in separate locations. One way to think about this is in terms of the quantum wave function. In quantum mechanics, the wave function of a multi-particle system is not a function defined over ordinary three-dimensional space. It is a function defined over configuration space, a mathematical space in which one dimension is assigned to every degree of freedom of every particle in the system. For two particles in three-dimensional space, the wave function lives in a six-dimensional configuration space. For a billion particles, the wave function lives in a space of 3 billion dimensions. The entanglement between particles corresponds to the wave function not factoring into independent parts for each particle. The whole system has a global quantum state that cannot be decomposed into independent states for its parts. This is deeply different from anything in classical physics. In classical mechanics, the state of a system of many particles is fully specified by giving the position and momentum of each particle individually. The overall state is a collection of individual states. In quantum mechanics, the overall state can be something that has no decomposition into individual particle states. The system as a whole has correlations that are not reducible to properties of its parts. This holism, the dependence of the whole on correlations that are irreducible to the properties of parts, is a feature of quantum mechanics with no classical analog. The holographic principle takes this holism further. If the information content of a region of space is encoded on its boundary surface, then the three-dimensional interior is not the fundamental level of description. The fundamental description is on the lower dimensional boundary. Processes that appear to be happening at different locations in the interior might be described by the same degrees of freedom on the boundary. What looks like spatial separation in the interior might correspond to something less neatly separated in the boundary description. Researchers working on quantum gravity have explored this in the context of the anti-de Sitter conformal field theory correspondence with striking results. Certain processes in the interior of an anti-de Sitter space, processes that from the interior perspective look like local gravitational phenomena, correspond to highly non-local operations on the boundary quantum field theory. Conversely, operations that are local on the boundary can correspond to things that are spread across the interior. The correspondence between interior and boundary scrambles our intuitions about what is happening where. It suggests that the association of specific physical processes with specific locations in space is not as fundamental as it seems. This line of thinking has led to specific proposals about how space-time itself emerges from more fundamental structure. Mark van Ramsdonk published a striking paper in 2010 arguing that entanglement is essential for the connectivity of space. He showed that in the context of the anti-de Sitter conformal field theory correspondence, reducing the entanglement between two regions of the boundary quantum field theory causes the corresponding geometry in the interior to split into disconnected pieces. Increase the entanglement and the connection strengthens. Remove the entanglement entirely and the regions become completely disconnected in the interior geometry. Entanglement in this framework is what holds space together. The connectivity of spatial geometry arises from quantum correlations between the underlying degrees of freedom. This is a radical proposal. It means that the smooth, continuous space we navigate is not a background container in which physics happens. It is an emergent feature arising from the pattern of quantum correlations in a more fundamental description. If you could dial down the entanglement in the quantum description of the universe, space would dissolve. This is not a metaphor. It is a specific mathematical claim with derivable consequences within well-defined theoretical frameworks. The implications for our everyday experience of space as something solid and persistent are unsettling in the best sense. The table you see across the room appears to be at a definite distance, occupying a definite region, sitting stably in three-dimensional space. Within the framework of emergent spacetime, this appearance reflects a highly entangled quantum state whose correlation structure gives rise to a geometric description that assigns definite distances and locations to objects. The table's position in space is not a primitive fact. It is an emergent description of a quantum state. The reason this emergent description is so reliable and stable for everyday objects is that large objects are composed of enormous numbers of particles in highly entangled states with their environments. This entanglement, through a process called decoherence, suppresses the quantum superpositions that are so prominent for isolated microscopic particles. When a particle interacts with its environment, its quantum state becomes entangled with the environment's quantum state. For all practical purposes, quantum superpositions for the particle alone cease to be observable. The different possibilities decohere into effectively separate classical histories. This is why the quantum weirdness of individual particles does not show up in the behavior of everyday objects. The entanglement with the environment suppresses it. Decoherence explains why quantum mechanics gives way to classical mechanics at large scales. It does not, however, explain why the particular measurement outcome we observe occurs rather than any other. Within the many worlds framework, all outcomes occur in separate branches. Within the Copenhagen framework, the question is not meaningful. Within other frameworks, different answers are given. But what decoherence does explain is why we do not see tables and chairs in quantum superpositions, why the world looks classical even though it is described by quantum mechanics at the fundamental level. The classical appearance of the world emerges from quantum mechanics through entanglement with the environment. The solid, stable, locally defined world of everyday experience is itself an emergent description that rests on a quantum foundation. Black holes provide perhaps the most striking laboratory for thinking about the fundamental nature of space, information, and reality. A black hole is not simply an exotic astronomical object. It is a regime in which the tensions between quantum mechanics and general relativity become acute, and in which the nature of spacetime is most severely tested. General relativity predicts that when enough mass is concentrated in a small enough region, the curvature of spacetime becomes so extreme that a boundary forms, the event horizon, from inside which nothing can escape. The spacetime geometry inside the event horizon is singular, in the sense that the equations of general relativity produce infinite curvature at a central point, called the singularity. This singularity is not a physical object, but a breakdown of the theory, a signal that general relativity is not adequate to describe what happens there. Physicists believe that a complete theory of quantum gravity, combining quantum mechanics with general relativity, would resolve the singularity and give a sensible description of the interior of a black hole. We do not yet have such a theory. String theory and loop quantum gravity are the two most developed candidates, but neither has yet produced a testable prediction that distinguishes it from alternatives, and neither has been confirmed experimentally. The nature of the singularity remains one of the deepest open questions in physics. What Hawking's work on black hole radiation revealed is that the conflict between quantum mechanics and general relativity already manifests outside the event horizon. The Hawking process, by which a black hole emits radiation through quantum effects near the horizon, implies that black holes eventually evaporate completely. An initial pure quantum state, a star before it collapses, evolves into a black hole that subsequently evaporates into thermal radiation. If the radiation is perfectly thermal and carries no information, then the initial pure state has evolved into a mixed state, a state described by thermal statistics rather than a specific quantum state. But quantum mechanics requires that pure states evolve only into pure states. Information cannot be truly destroyed. This is the information paradox. Physicists have been working to resolve the paradox since Hawking first identified it in the 1970s. Progress has been substantial in recent years. Work by Ahmed Almhiri, Netta Engelhardt, Henry Maxfield, Jeff Pennington, and others has used the holographic principle and techniques from quantum information theory to argue strongly that information is preserved. Their calculations show that the entropy of the Hawking radiation follows a specific curve, first rising as the black hole emits, then falling as the correlations in the radiation begin to reflect the information about what fell in. This curve, known as the Page curve, is what unitary quantum mechanics requires for information to be preserved. The calculations suggest that the interior geometry of the black hole must be modified in ways that are difficult to understand classically, but that the net effect is to preserve information in the outgoing radiation. The precise mechanism remains unclear and is an active area of research, but the convergence of independent calculations from multiple groups using different methods toward the conclusion that information is preserved has shifted the consensus significantly. The black hole information paradox is not yet solved in the sense of having a complete, satisfying mechanical description, but the evidence points strongly toward resolution, and that resolution involves information being the truly conserved quantity in physical processes. The concept of entropy, which is the thermodynamic measure of disorder and is intimately related to information content, plays a central role in all of these considerations. The second law of thermodynamics states that the total entropy of a closed system never decreases. Disorder always increases over time. This is the thermodynamic arrow of time, the reason why the past and future feel different, why things break but do not spontaneously reassemble. But the microscopic laws of physics are time reversible. The fundamental equations of quantum mechanics are symmetric with respect to time reversal. How can an irreversible macroscopic tendency arise from reversible microscopic laws? The answer involves both the initial conditions of the universe and the relationship between information and probability. The early universe had extraordinarily low entropy, a highly ordered initial state. As the universe evolved, entropy increased, as the second law demands. The direction of increasing entropy defines what we call the future. We remember the past and not the future, because the past corresponds to the direction of lower entropy from which we evolved, and our memories are records of that evolution. If the universe had begun in a high entropy state, the second law would still hold, but there would be no discernible direction to time. The origin of the low entropy initial state of the universe is one of the deepest mysteries in cosmology. It is deeply puzzling because a randomly chosen universe would almost certainly have much higher entropy than the universe we observe. The probability of the specific low entropy initial configuration of our universe, compared to all possible initial configurations with the same energy, is fantastically small. Why did the universe begin in such an improbable state? This question has no universally accepted answer, though various proposals have been made involving inflation, the quantum creation of universes, and anthropic selection. Inflation is the best supported of these proposals. Inflation is a period of extremely rapid exponential expansion that most cosmologists believe occurred in the first tiny fraction of a second after the Big Bang. During inflation, a region of space, much smaller than an atomic nucleus, expanded to a scale comparable to the observable universe in an extraordinarily short time. Inflation smooths out any initial irregularities, explaining why the universe appears uniform on large scales. It also stretches microscopic quantum fluctuations to macroscopic scales, seeding the small density perturbations that later grew into the cosmic web of galaxies we observe. Inflation has been tested through observations of the cosmic microwave background radiation, the afterglow of the hot, dense early universe, and the predictions of inflationary models have been confirmed with remarkable precision. But inflation does not fully explain the low entropy initial state. It explains why the universe is smooth on large scales, but does not obviously explain why the quantum field driving inflation was in a specific low entropy configuration to begin with. The question is pushed back one step, but not resolved. The deep question of why there was a low entropy beginning remains open and is connected to questions about the nature of time, the quantum creation of universes, and whether the universe is part of a larger multiverse. The multiverse is not a single idea, but a family of related proposals. In inflationary cosmology, the rapid expansion may continue forever in most regions of space, while slowing down and creating bubble universes in others. Our observable universe would be one such bubble, one region where inflation ended and conventional Big Bang evolution began. In the surrounding inflationary space, other bubbles form with potentially different properties, different values of physical constants, different laws at the low energy level. This eternal inflation scenario implies the existence of a vast and potentially infinite multiverse of bubble universes. The string theory landscape takes this further. String theory predicts an enormous number of possible low-energy configurations, different ways that extra dimensions can be compactified, and different values that constants can take in the resulting four-dimensional physics. The number of distinct possibilities is estimated to be on the order of 10 to the 500, a number so large it defies meaningful comparison to anything in ordinary experience. If eternal inflation populates different bubble universes with different configurations from this landscape, then we exist in one bubble with one configuration out of an astronomical number of possibilities. This landscape picture makes the fine-tuning of physical constants less mysterious. Constants, like the cosmological constant, which governs the energy density of empty space, appear to be finely tuned to values that permit complex structures like stars, planets, and ultimately observers. The observed value of the cosmological constant is roughly 120 orders of magnitude smaller than naive estimates from quantum field theory predict. 120 orders of magnitude is not a small discrepancy. It is the most extreme unexplained discrepancy in all of physics. In a landscape of many universes with different values, observers will only find themselves in universes where conditions are compatible with their existence. We observe a small cosmological constant because only universes with a small cosmological constant permit observers to exist. This anthropic reasoning is controversial. It explains fine-tuning without identifying any dynamical mechanism that selects for small values. Critics argue that it is not a scientific explanation in the usual sense because it does not generate testable predictions. Supporters argue that it is a legitimate use of conditional probability, reasoning about what we should expect to observe, given that we are observers. The debate is ongoing. What connects all of these threads? The non-locality of quantum entanglement, the emergence of space-time from quantum correlations, the holographic encoding of information, the preservation of information in black holes, the arrow of time and its connection to entropy, the fine-tuning of constants, and the possible existence of a multiverse is a set of deep questions about the nature of information and its relationship to physical reality. Information, which in the context of physics means the specific configuration of a system as opposed to all other possible configurations, appears to be conserved, to be the fundamental currency of physical processes, and potentially to be the primary ingredient from which space, time, and matter emerge. Whether this perspective will lead to a complete theoretical revolution of the kind that quantum mechanics represented in the early 20th century is not known. The revolution, if it comes, may require conceptual resources that do not yet exist. History suggests that the breakthroughs that matter most are not incremental refinements of existing ideas, but genuine reconceptualizations that make previously impossible questions answerable. The development of quantum mechanics did not just answer questions within classical physics. It introduced a new framework in which old questions were reformulated and new ones became visible. The relationship between quantum mechanics and general relativity remains unresolved, and resolving it will likely require another such reconceptualization. The tools available to researchers today are more powerful than those of any previous era. Gravitational wave observatories can detect the merger of black holes a billion light-years away. Quantum computers are being built that can maintain quantum coherence across hundreds of qubits. Particle accelerators probe matter at energy scales that were completely inaccessible a generation ago. Cosmological surveys are mapping the distribution of galaxies across the observable universe with unprecedented precision. The cosmic microwave background has been measured to the point where the limiting factor is the fundamental quantum noise of the photons themselves. Numerical simulations of quantum gravity models can test ideas that were previously purely theoretical. These tools are already producing results that constrain and guide theory. The detection of gravitational waves from black hole mergers provided a new way to measure the Hubble constant, the expansion rate of the universe. This independent measurement added to the tension between different measurements of the expansion rate, a tension called the Hubble tension that has now reached a level of statistical significance demanding explanation. The most precise measurements of the cosmic microwave background give one value, Measurements of distances to nearby galaxies using standard candles like Cepheid variable stars and type Ia supernovae give another value. The two disagree by roughly 9%, with an uncertainty far too small to dismiss as measurement error. Either one of the measurement methods has an unidentified systematic error, or the standard cosmological model is incomplete. The Hubble tension may be resolved by better calibration of astronomical distance measurements, or it may be pointing to physics beyond the standard cosmological model. Proposals involving new particles, modifications of general relativity at cosmological scales, or changes in the properties of dark energy have all been explored. The resolution, when it comes, may or may not require new fundamental physics, but the discrepancy is real and currently unexplained, and it sits alongside the information paradox, the origin of low-entropy initial conditions, the nature of dark matter, and the measurement problem in quantum mechanics as a set of open questions where the understanding is known to be incomplete. Dark matter deserves particular attention because its existence is inferred from extraordinarily robust and diverse evidence, and yet its nature remains completely unknown. Galaxies rotate in a way that cannot be explained by the gravity of their visible matter. The speed at which stars orbit the galactic center does not decrease at large distances from the center, as it should if most of the mass is concentrated near the center. Instead, rotation curves remain flat at large radii, implying that additional mass exists in extended halos surrounding galaxies. The gravitational lensing of background galaxies by galaxy clusters reveals more mass than is visible. The formation of large-scale structure in the universe, the growth of galaxy clusters and filaments from small initial fluctuations, requires an additional component of matter that does not interact electromagnetically and that moves slowly enough to clump under gravity. All of these independent lines of evidence converge on the existence of dark matter, making up roughly 27% of the total energy content of the universe. But the identity of the particles composing dark matter is unknown. Weakly interacting massive particles were the leading candidate for decades, motivated by theoretical considerations in particle physics beyond the standard model. But searches at the Large Hadron Collider, underground detectors, and gamma-ray observatories have not found them. Alternative candidates including axions, sterile neutrinos, and various other particles are being pursued, but none has been confirmed. There remains the possibility that dark matter is not a particle at all. Modified theories of gravity, which alter the relationship between matter distribution and gravitational force at certain scales, can reproduce some of the observational signatures attributed to dark matter. But they struggle to explain all of the evidence, particularly the pattern of temperature fluctuations in the cosmic microwave background and the detailed structure of galaxy clusters. The evidence for a particle-based dark matter explanation remains stronger than the alternatives, but the particle itself is unknown. Dark energy is even more mysterious. The accelerating expansion of the universe, discovered in 1998 from observations of distant type Ia supernovae, requires a component with negative pressure that causes space to expand faster and faster over time. The simplest explanation is the cosmological constant, a constant energy density throughout space and time. But, as noted earlier, the observed value of the cosmological constant is 120 orders of magnitude smaller than what quantum field theory predicts for the energy density of empty space. No satisfactory explanation for this discrepancy exists. It is one of the most profound unsolved problems in fundamental physics. Alternative explanations involving dynamical fields, called quintessence models, predict that the equation of state of dark energy may vary slowly over time. New cosmological surveys are designed to detect or rule out such variation. The Dark Energy Spectroscopic Instrument, which began full science operations recently, is measuring the spectra of tens of millions of galaxies to reconstruct the expansion history of the universe in unprecedented detail. If dark energy is not simply a cosmological constant, but something that varies over time, these surveys should reveal the signature. The questions surrounding dark matter, dark energy, quantum gravity, the Hubble tension, and the information paradox are not isolated puzzles. They are connected pieces of an incomplete picture. A successful theory of quantum gravity would likely illuminate the nature of black hole singularities and the information paradox. It might also shed light on the nature of dark energy and the cosmological constant. The origin of low-entropy initial conditions is connected to the overall structure of the universe and potentially to questions about whether our universe is part of a larger multiverse. The measurement problem in quantum mechanics is connected to deep questions about the relationship between consciousness and reality, about what it means to make an observation, and about whether the wave function is a complete description of physical reality or something more limited. These are not separate problems that can be solved independently. They are facets of a single large question about the nature of reality at the deepest level. And the scientific community pursuing these questions is not working in isolation. Quantum information theorists collaborate with string theorists. Cosmologists collaborate with particle physicists. Neuroscientists collaborate with philosophers. The questions at the frontier of one field are often precisely the questions that another field needs to answer. The emerging picture of reality as arising from quantum information, with space-time and matter as emergent features of a deeper informational structure, is not the product of any single discipline, but of a convergence across multiple fields. What science can say, at this point in its development, is the following. The universe does not consist of objects with definite properties sitting quietly in space. It consists of quantum states whose properties are only realized through interaction. The geometry of space-time appears to emerge from quantum correlations rather than being a fundamental background. Information is conserved through physical processes, even in extreme environments like black holes. The experience of reality is a construction built by the brain rather than a direct perception of an external world. And the fundamental nature of what generates that construction, what physical reality ultimately is at the deepest level, remains an open question. This is not a counsel of ignorance. It is a description of the actual state of scientific knowledge, which is vastly richer and more detailed than it was 100 years ago. The questions that remain open are harder than the ones that have been answered, and their resolution will require greater effort, more precise experiments, and likely new conceptual frameworks. But the history of physics shows that these kinds of revolutions do occur. They occurred with Newton, with Maxwell, with Einstein, with Bohr and Heisenberg and Dirac. The current situation, with quantum mechanics and general relativity sitting unreconciled and both demonstrably incomplete, is precisely the kind of situation from which revolutions emerge. The scientists working on these questions are not waiting for revelations. They are building better mathematical tools, designing more sensitive detectors, pushing the precision of existing measurements, and following the logical consequences of established theories into previously unexplored territory. The results of that work, over the coming decades, will either confirm the emerging picture or overturn it. Either outcome would be one of the most significant developments in the history of science. The universe is old. Roughly 13.8 billion years have elapsed since the Big Bang, a span of time so vast that human civilization is a rounding error. In that time, matter formed stars. Stars forged heavier elements. Those elements coalesced into planets. On at least one of those planets, the chemistry of life emerged. And over billions of years, that life evolved into creatures capable of asking questions about the nature of reality. The fact that the universe is knowable, that its structure is accessible to rational investigation, that the laws governing elementary particles at femtometer scales also govern the large-scale structure of the cosmos, is itself a profound and as yet unexplained feature of the world we inhabit. The path from subatomic particles to conscious observers capable of quantum mechanics and general relativity is long and winding, but it is a path that exists. We are here. We are asking these questions. And the questions themselves, about whether the universe is real in any observer-independent sense, about what consciousness is and where it comes from, about whether space and time are fundamental or emergent, about whether information is the deepest level of reality, are questions that the universe, through the evolution of conscious observers within it, has generated the capacity to ask. Whether it has generated the capacity to fully answer them remains to be seen. Consider what it actually means for a particle to lack a definite property before measurement. This is not the same as saying the property exists, but we do not know it. The experiments ruled out that interpretation. If the spin of a particle were simply unknown to us, but had a definite value that was determined at the moment the two particles separated, the correlations between measurements on distant particles would obey specific mathematical limits. The experiments found correlations that exceed those limits. This is not a matter of incomplete information or measurement error. The particle genuinely does not have a definite spin value until a measurement is made. This is what the physics says, stripped of interpretive hedging. The closest analogy that conveys the strangeness is to imagine a coin that has no definite state of heads or tails until the moment you look at it. Not a coin whose state you do not know, but a coin that does not yet have a state. The state comes into being through the act of looking, and if you have two such coins that are entangled, when you look at one and find heads, the other instantly becomes tails, wherever it is. The instant correlation is not because the coins carried their outcomes from the start. That interpretation predicts correlations that are weaker than what experiments actually find. The correlation is something else, something without a good classical intuition, because nothing at the classical level works this way. There is something genuinely new in quantum mechanics. Not new in the sense of being more complicated than classical physics, though it is. New in the sense of being qualitatively different in a way that forces revision of the most fundamental categories we use to describe reality. The categories of definite value, local causation, and observer-independent property, categories so basic they seem like preconditions for any description, rather than assumptions that could turn out to be wrong. Turn out to be wrong? Or at least inapplicable at the most fundamental level. The story of how this realization developed over the 20th century is itself remarkable. The founders of quantum mechanics, including Bohr, Heisenberg, Schrödinger, and Dirac, created the mathematical formalism in the 1920s. The formalism worked brilliantly. Its predictions for the spectra of atoms, for the behavior of electrons in magnetic fields, for the probabilities of radioactive decay, were confirmed with high precision. But what the formalism meant, what picture of reality it was describing, was a matter of intense and unresolved disagreement from the beginning. Einstein was never satisfied with the Copenhagen interpretation, the view that quantum mechanics is a complete description of reality and that asking about what is happening between measurements is meaningless. He felt, deeply and consistently, that a complete theory of nature must describe what things are, not just what measurements will show. His discomfort culminated in the 1935 paper with Boris Podolsky and Nathan Rosen, the EPR paper, which described a thought experiment designed to show that quantum mechanics must be incomplete. The argument used entanglement, what Einstein called spooky action at a distance, to show that if measurement outcomes on distant particles can be correlated instantaneously, then either quantum mechanics is incomplete or influences travel faster than light. Einstein rejected the second option. He believed local realism was correct and concluded quantum mechanics was incomplete, that there were hidden variables not captured by the wave function that determined measurement outcomes in advance. Bohr responded that the EPR argument rested on a mistaken conception of what it means for a physical quantity to have reality. The disagreement between Einstein and Bohr was never resolved in their lifetimes. It required Bell's mathematical theorem in 1964 and the subsequent experiments of Clauser, Aspect, and Zeilinger to settle it experimentally. The experiment showed Einstein was wrong, or at least that local realism is false. Whether this vindicates Bohr's position depends on which interpretation of quantum mechanics you favor, since there are interpretations that preserve realism at the cost of locality and others that abandon both. But the experiments definitively ruled out local realism. What survived was the quantum formalism itself, the mathematical apparatus of wave functions, operators, and probabilities, which continues to make extraordinarily accurate predictions, and whose practical applications now permeate modern technology. Transistors, laser diodes, magnetic resonance imaging, and semiconductor devices all operate on principles that cannot be understood without quantum mechanics. Quantum computing, which exploits quantum superposition and entanglement to perform computations impossible for classical computers, is currently being built at scales of hundreds to thousands of quantum bits. Quantum cryptography uses the no-cloning theorem, a fundamental feature of quantum mechanics, to guarantee theoretically unbreakable encryption. The technology built on quantum mechanics is woven through modern civilization, even though the philosophical questions about what quantum mechanics means remain unresolved. This is an unusual situation. A theory can be practically indispensable and theoretically understood at the level of predictive power, while remaining philosophically opaque at the level of what it says about the nature of reality. Classical mechanics was both predictively powerful and philosophically transparent, or at least it seemed so. Its picture of particles moving through space under definite forces was easy to visualize and seemed to correspond to an objective reality independent of observers. Quantum mechanics is predictively superior in every domain, where both theories can be applied, but its picture of reality is obscure in a way that classical mechanics is not. The obscurity is not a limitation of our understanding that will eventually be resolved by more information. It reflects something genuinely strange about the physical world. One attempt to clarify the situation is the decoherence approach to the measurement problem. Decoherence is not itself an interpretation of quantum mechanics, but a physical process that helps explain the quantum to classical transition. When a quantum system interacts with its environment, which for any macroscopic object is happening continuously and unavoidably, the system becomes entangled with a vast number of environmental degrees of freedom. The quantum superpositions that make individual particles behave so strangely survive only as long as the particle is isolated. As soon as the environment becomes entangled with the particle, the superposition spreads across a system so large and complex that the interference effects that characterize quantum behavior become unmeasurable. What remains is a statistical mixture that behaves like a classical probability distribution over definite outcomes. Decoherence explains why Schrödinger's cat, the famous thought experiment involving a cat whose life or death is correlated with a quantum event, would in practice be found definitely alive or definitely dead when examined, not in a superposition of alive and dead. The cat's quantum state becomes entangled with the environment through the enormous number of air molecules, photons, and thermal fluctuations continuously interacting with it. The decoherence time for a macroscopic object like a cat is extraordinarily short, far shorter than any experimental access is possible. By the time you open the box, the quantum superposition has already decohered into an effective classical mixture. This is not a collapse in the sense of the Copenhagen interpretation. The wave function does not literally collapse. The apparent definiteness arises from the spreading of entanglement to the environment, making the coherences practically unmeasurable. But decoherence alone does not fully resolve the measurement problem. It explains why outcomes appear classical, but does not explain why a specific outcome occurs rather than another. In the many worlds framework, all outcomes occur in different branches, and decoherence explains why the branches do not interfere with each other and why observers in each branch see a single definite outcome. In other frameworks, different answers are given. The philosophical question of why any particular outcome is experienced remains. Decoherence is a crucial piece of the puzzle, but not the final piece. The connections between quantum mechanics and thermodynamics, particularly the relationship between entropy, information, and the direction of time, run deeper than they might initially appear. The thermodynamic entropy of a system and the information theoretic entropy developed by Claude Shannon in 1948 are mathematically the same quantity, related by Boltzmann's constant. Shannon entropy measures the number of bits required to describe the state of a system, which is equivalent to the logarithm of the number of possible states the system could be in given what you know about it. Boltzmann entropy measures the number of microscopic configurations compatible with a given macroscopic state. They are the same mathematics applied to different contexts. This correspondence is not an accident. Thermodynamic irreversibility, the tendency of entropy to increase, is a statistical consequence of the enormous number of degrees of freedom in macroscopic systems. There are astronomically more ways for energy to be distributed randomly among many particles than concentrated in an ordered pattern. Given any starting configuration, the system will almost certainly evolve toward higher entropy states simply because they are overwhelmingly more numerous. The arrow of time, the asymmetry between past and future in our experience, reflects this statistical tendency. But statistical inevitability is not the same as logical inevitability. The microscopic laws are time reversible. A movie of particles bouncing off each other run backward is also a valid solution to the equations of motion. The irreversibility is statistical, emerging from the overwhelmingly greater number of high entropy states, and the initial low entropy state of the universe, from which all subsequent entropy increase proceeds, is itself unexplained. It is a boundary condition that physics accepts but cannot, at present, derive. Roger Penrose has argued that the low-entropy initial condition of the universe is itself a profound mystery requiring explanation, not just acceptance. His estimation of the probability of the specific initial configuration of our universe, treating all possible initial configurations as equally likely, produces numbers that are mind-bending. The probability, expressed as a fraction, has a denominator with more zeros than there are elementary particles in the observable universe. This is not a rounding error or a matter of different assumptions. It is a robust consequence of thermodynamic reasoning applied to cosmological initial conditions. The specific ordered initial state of our universe is breathtakingly improbable if one treats all possible initial states as equally accessible. Penrose proposed that the resolution requires a physical mechanism that selects for low-entropy initial conditions, something in the laws of physics that produces order at the beginning. His specific proposal, called conformal cyclic cosmology, involves a series of aeons, each consisting of a Big Bang followed by an expansion, with the end state of one aeon acting as the initial condition for the next. The mechanism that connects them involves the conformal symmetry of massless particles and specific features of the very large and very small scale behaviors of physics. It is a speculative proposal, not yet confirmed by observation, but it represents a serious attempt to explain rather than simply assume the low-entropy initial condition. Other proposals approach the problem differently. The Hartle-Hawking no-boundary proposal treats the very beginning of the universe as a quantum process in which time itself emerges from a four-dimensional geometry with no boundary. In this framework, asking what came before the Big Bang is like asking what is south of the South Pole. The question does not have an answer because the geometry of space-time near the beginning is such that the temporal direction smoothly transforms into a spatial direction, leaving no temporal boundary, and hence, nothing before. The universe begins not from a singularity with sharp initial conditions, but from a smooth quantum geometry that naturally produces low entropy. The Hartle-Hawking state is mathematically elegant and generates specific predictions for the quantum fluctuations in the early universe, which in principle could be tested through precision measurements of the cosmic microwave background. Whether those predictions are confirmed is a matter of active observational investigation. But the fundamental question of why the universe has the specific character it does, why it began in a low-entropy state, why its laws take the specific form they do, and why there is something rather than nothing, remains open and may be the deepest open question in all of science. The possibility that our universe is just one among many, that what we call the laws of physics are contingent features of one particular universe in a vast ensemble rather than necessary features of reality, has implications for what kind of explanation is possible. If there is no higher-level law that selects the constants and laws of our universe, if they are simply the values that happen to exist in this particular bubble of a multiverse, then asking why they have these values rather than others is like asking why you were born in this particular country rather than another. The question has an answer in terms of history and contingency, but not in terms of logical necessity. This represents a potential shift in scientific epistemology. Science has traditionally sought universal laws, principles that hold everywhere and at all times, and that could not be otherwise. The multiverse picture, if correct, implies that some of what we thought were universal laws are actually local contingencies. The charge of the electron, the mass of the Higgs boson, the strength of gravity, the cosmological constant. These might be values that happen to take their specific magnitudes in our bubble universe, while taking different magnitudes in other bubbles. Explaining them becomes a matter of statistics and observer selection rather than fundamental derivation. Some physicists find this deeply unsatisfying, a capitulation to unintelligibility disguised as explanation. Others regard it as a natural extension of the Copernican principle, which has progressively moved humanity away from the assumption that our location in the universe is special. Earth is not the center of the solar system. The solar system is in an ordinary location in the Milky Way. The Milky Way is one galaxy among hundreds of billions. Perhaps our universe is one among an enormous or infinite number of universes, each with its own laws and constants. The discomfort this generates is understandable, but discomfort is not a scientific argument. The specific question of whether the multiverse is scientifically accessible, whether any observation could in principle confirm or refute it, is serious and contested. If all observable effects are confined to our own bubble universe, the other bubbles are not just unobserved, but in principle unobservable. Some physicists argue that an unobservable entity is not a scientific entity at all, and that multiverse theories are metaphysics dressed in scientific language. Others argue that the theoretical framework generating the multiverse prediction is testable through its other consequences, even if the other universes themselves are not directly accessible. The Large Hadron Collider and cosmological surveys can constrain inflationary models and aspects of string theory landscape predictions, providing indirect tests of the broader framework. This is itself a philosophical question about the demarcation of science, about what counts as a legitimate scientific explanation, and about how inference to the best explanation works when the entities being inferred are unobservable in principle. The philosophy of science has sophisticated tools for analyzing these questions, and the current situation in cosmology has generated productive dialogue between physicists and philosophers at a level of depth that has not been seen since the foundational debates over quantum mechanics in the early 20th century. The question of whether science can say anything definitive about consciousness, about its nature, its relationship to physical processes, and its role in the quantum measurement problem remains genuinely open. The hard problem of consciousness, the question of why physical processes in the brain are accompanied by subjective experience, is hard in a specific technical sense. It is not just that we do not yet know the answer. It is that we do not have a clear picture of what kind of answer would be satisfying, what form a solution would take, or how we would recognize a solution if we found one. The explanatory gap between objective descriptions of brain processes and the subjective reality of experience is a real philosophical gap, not just a temporary gap in knowledge. When neuroscience fully characterizes the neural correlates of consciousness, when we know exactly which patterns of neural activity accompany which conscious states, the question of why those physical processes feel like anything at all will remain. The correlation can be mapped, but the connection, why one side of the correlation involves an inner experience at all, is not explained by listing the other side. Integrated information theory attempts to address this by defining consciousness in terms of a quantity that can in principle be measured in physical systems. Consciousness, on this view, is identical to integrated information. This is not a description of a correlation, but an identity claim. A system is conscious to the extent that it integrates information. The advantage of this approach is that it makes consciousness a continuous graded property that in principle any system can possess to some degree. The disadvantage is that it seems to imply that some simple systems, like a grid of logic gates arranged in a specific way, should be more conscious than a human brain, which most people find counterintuitive. Global workspace theory makes a different claim. Consciousness corresponds to the global broadcast of information, to information being made available simultaneously to many different cognitive processes. This explains why anesthetics that disrupt global broadcasting produce unconsciousness, and why certain types of brain damage produce loss of consciousness while leaving many cognitive functions intact. But it leaves open why the global broadcast feels like anything, returning us to the hard problem. The neuroscientist Stanislas Dehaene has argued that the global workspace theory makes testable predictions about which kinds of mental processing reach consciousness and which do not, predictions that have been confirmed in laboratory studies. The theory is scientifically productive, even if it does not solve the hard problem in a philosophical sense. This may be the best science can do. The hard problem may be genuinely intractable within any third-person scientific framework, because the subjective character of experience is precisely what resists third-person description. The philosopher Thomas Nagel argued in his famous 1974 paper that there is something it is like to be a bat, an inner, experiential quality of echolocation and darkness that no amount of objective description of bat neuroscience can capture. Nagel's point was that consciousness, by its very nature, has a subjective character that is inaccessible to purely objective scientific description. This is not a temporary limitation of current neuroscience, but a logical feature of the relationship between subjective and objective descriptions. This argument continues to be influential and has not been definitively refuted, though it has been extensively contested. The possibility that consciousness is itself a fundamental feature of reality, rather than an emergent property of sufficiently complex physical systems, is taken seriously by some philosophers and physicists. Panpsychism, The view that some form of proto-consciousness or experience is a fundamental feature of all physical reality and not just brains, has ancient roots and has been revived in sophisticated contemporary forms. The philosopher David Chalmers and the neuroscientist Christoph Koch have both argued that some form of panpsychism may be required if the hard problem is to be solved. The idea is that if experience cannot emerge from purely non-experiential physical processes, then the substrate of experience must be there from the start, at the level of fundamental physics. Integrated information theory, on its panpsychist reading, implies that even simple physical systems have a tiny degree of consciousness. This is a radical claim, but it has a logical structure that makes it harder to dismiss than the word panpsychism might initially suggest. If consciousness is a fundamental property correlated with integrated information processing, and if all physical systems process information to some degree, then some form of experience is ubiquitous. Whether this is the right approach to consciousness is far from established, but it represents a serious philosophical position, not mystical speculation. The relationship between all of these ideas, quantum mechanics, consciousness, information, and the nature of reality, is beginning to crystallize into something that might be called a new scientific worldview, though that is a premature description. What is clearer is that the old worldview of a world made of solid objects with definite properties, governed by deterministic local laws, and fully described by physics independent of any observer, is no longer adequate. The new view, still taking shape, involves information as the fundamental substrate, quantum entanglement as the glue of spatial geometry, consciousness as something deeply connected to the physics of measurement and information, and reality at the deepest level as something that may require new categories not yet invented. The physicist John Wheeler spent the later part of his career pursuing what he called the meaning circuit. He believed that the universe begins in some primordial quantum soup of possibilities. Observers emerge over time through the evolution of matter. Those observers make measurements, participate in the physical world, and through their observations bring definite properties into existence. The observations are recorded in physical memory, whether neural, written, or encoded in the structures of civilization. That record of observations, that information about what has been observed, is what Wheeler called meaning. The universe gives rise to observers who give rise to meaning, which in some participatory sense creates the universe. He called this participatory universe and described it with his phrase, "it from bit." This is speculative, and Wheeler acknowledged it as such. But it captures something real about the quantum measurement problem. In quantum mechanics, the observer is not a passive spectator, but a participant. The choice of what to measure, which property to examine, determines what property comes into existence. This is not magic or mysticism. It follows logically from the quantum formalism. The act of measurement is a physical interaction that brings about a specific quantum state, where previously there was a superposition. The observer's choice does not create the world from nothing, but it does determine which aspects of the world's potential become actual. There is a specific and beautiful experiment that illustrates this participation dramatically. It is called the delayed choice experiment, and it was proposed by Wheeler and subsequently realized in the laboratory. In the standard double-slit experiment, a particle is sent toward a barrier with two slits. If both slits are open, and no detector monitors which slit the particle goes through, the particle exhibits an interference pattern on the detection screen, indicating it went through both slits simultaneously as a wave. If a detector monitors which slit the particle passes through, the interference pattern disappears, and the particle behaves as if it went through one slit only, like a classical particle. In Wheeler's delayed choice version, the decision about whether to monitor which slit the particle passes through is made after the particle has already passed through the slits but before it reaches the detection screen. The result is the same. If you decide to check which slit the particle used, the interference pattern disappears, even though the particle has already passed through the slits before the decision was made. If you decide not to check, the interference pattern appears. The measurement choice, made after the particle is already past the slits, retroactively determines whether the particle behaved as a wave or a particle at the slit. This is not faster-than-light communication and cannot be used for it. The particle's behavior is not determined in advance. The distribution of particles over many experimental runs arranges itself into the pattern appropriate to the measurement choice. as if the particles collectively knew in advance what choice would be made, even though the choice is made after they pass the slits. The quantum formalism accounts for this correctly, but the intuitive picture of a particle existing in a definite state at the slits, in a state that is later disturbed by measurement, is simply wrong. The particle's history is not settled until the measurement is complete. There are experimental versions of this experiment that extend the principle over cosmic distances. Using light from distant quasars as sources and galactic gravitational lenses as the two paths, physicists have proposed versions of the delayed choice experiment in which the choice about which path the photon took would be made billions of years after the photon embarked on its journey. The physics does not change. The correlations would arrange themselves correctly regardless of when the choice is made. Time, in quantum mechanics, does not work the way common sense suggests. The history of a quantum system is not written as it happens and then fixed. It is fixed only when a measurement settles it. This connects to a profound question about the nature of time itself. In ordinary experience, time flows from past to future. The past is fixed and inaccessible to change. The future is open. The present is where things happen. This temporal structure is so deeply embedded in experience that it seems like a necessary feature of reality, not an assumption that could be questioned. Yet the fundamental equations of physics, both quantum and classical, are to varying degrees symmetric in time. There is no intrinsic distinction in the equations between past and future. The direction of time we experience is not written into the laws of physics, but emerges from the statistical tendency toward increasing entropy, combined with the specific low-entropy initial condition of our universe. If time's arrow is a statistical emergence from time-symmetric laws, then the past-future distinction we experience so vividly is itself an emergent feature of our macroscopic perspective, not a fundamental feature of physical reality. At the level of individual quantum interactions, there is no preferred direction of time in the physical equations. The asymmetry emerges at the level of statistical collections of many particles, where the overwhelming preponderance of states with higher entropy ensures that systems almost always evolve toward higher entropy, which we call the future. Carlo Rovelli, in his work on loop quantum gravity and in his broader reflections on the nature of time, has argued that time as we experience it, as a flowing directed progression from past to future, is a composite phenomenon built from several different physical ingredients. There is duration, the fact that processes take time. There is direction, the asymmetry between before and after. There is flow, the sense that the present is always moving. And there is the now, the present moment as something that exists globally throughout space. Rovelli argues that the last of these, the global now, is an illusion. The special theory of relativity already showed in 1905 that simultaneity is relative, that two events that are simultaneous in one reference frame are not simultaneous in another. There is no universal present that exists throughout space at a single instant. The present is always local. Building on this, Rovelli argues that time is ultimately a relational concept, not something that flows against a fixed background, but something that describes the relationships between the changing states of physical systems. At the quantum gravitational level, in the regime where quantum mechanics and general relativity must both apply, there may be no fundamental time variable at all. The equations governing quantum gravity, in some approaches, are timeless. What we experience as time emerges from the entanglement between physical systems and what functions as a clock in our environment. Time is not fundamental, it emerges. This is not a position unique to Rovelli or to loop quantum gravity. Some approaches to quantum cosmology similarly suggest that the universe at the fundamental level is described by a timeless wave function, and that time emerges only at the level of approximation relevant to observers embedded within the universe and interacting with their environments. The timeless picture is conceptually challenging because our experience of reality is structured entirely around time. Every perception, every thought, every action occurs in time. To be told that time is not fundamental, but emergent from something timeless, is to be told that the most basic structure of experience is not the most basic structure of reality. And this brings the narrative full circle. The gap between the structure of experience and the structure of physical reality, the gap that Parmenides identified philosophically 2,500 years ago, the gap that neuroscience has confirmed empirically, The gap that quantum mechanics has made precise and experimentally verifiable is real and deep. The world as experienced is not the same as the world as described by the best physical theories we have. The experienced world has solid objects with definite properties, local causation, a clear direction of time, and a unified present shared by all observers. The physical world, as best understood, has quantum states without definite properties before measurement, non-local correlations between entangled particles, a time direction that emerges statistically rather than fundamentally, and no universal simultaneity. The brain constructs the experienced world from the physical world, building a model that serves navigation, prediction, and survival. The model is extraordinarily good at these purposes. But it is a model, and like all models, it simplifies, filters, and interprets. The features it preserves are the features that matter for the purposes it was built to serve. The features it hides are the features that only become visible through precise instrumentation, controlled experiments, and rigorous mathematical analysis. The history of science is the history of building better tools for seeing beyond the model, for probing the physical world at scales and precisions that the biological senses cannot access. What those tools have revealed is a physical world that is fundamentally quantum mechanical, informationally structured, non-locally correlated, and in several specific respects, not locally real. It is a world in which space-time geometry emerges from quantum entanglement, in which information is conserved through processes including black hole evaporation, in which the act of measurement brings definite properties into existence rather than simply revealing properties that already existed, and in which the nature of consciousness and its relationship to the physical substrate remains one of the deepest open questions. These are not comfortable conclusions. They require revising intuitions that feel fundamental, but the history of science is replete with exactly this kind of revision. The Earth moves around the Sun, not the reverse. Time slows near massive objects and moving at high speeds. Matter and energy are interconvertible. Evolution produced complex life from simple chemistry. Each of these truths required abandoning deeply held intuitions, and each time the intuitions were found to be wrong, the resulting understanding was richer, stranger, and more illuminating than what it replaced. There is no reason to think the current situation is different. The intuitions being challenged now about the definiteness of properties before measurement, about the local causation of physical effects, about the fundamental nature of space and time, about the relationship between experience and physical reality, are deeply held and deeply embedded in the way we think about the world. They will not be easy to revise. They may require conceptual breakthroughs that have not yet occurred, but the evidence demanding their revision is robust, precise, and growing. And the reward for successful revision, a clearer and more accurate picture of what physical reality actually is, would be one of the most significant achievements in the history of human understanding. The way science progresses toward questions this deep is worth examining carefully. Progress is not uniform. It proceeds through long periods of incremental refinement punctuated by occasional conceptual revolutions that reframe entire fields. Thomas Kuhn described this in his 1962 work on the structure of scientific revolutions, identifying periods of normal science, in which researchers work within an accepted framework and accumulate results, and periods of crisis, when accumulated anomalies can no longer be accommodated within the existing framework and a new framework is required. The current situation in fundamental physics has the character of a crisis in the Kuhnian sense. The two most successful theories in the history of science, quantum mechanics and general relativity, are mutually incompatible at the mathematical level. General relativity describes space-time as a smooth, continuous, dynamical geometry. Quantum mechanics describes fields and particles as quantized, operating through probabilities and superpositions. Combining them into a consistent framework has proven extraordinarily difficult. The attempts that have progressed furthest, string theory and loop quantum gravity, make different assumptions, use different mathematical languages, and have not yet made contact with experiment in a way that would distinguish one from the other or from alternatives. String theory proposes that the fundamental constituents of nature are not point particles but extended one-dimensional objects, strings, vibrating in different modes. The different vibrational modes correspond to different particles. The theory requires extra dimensions of space beyond the three we experience, compactified at scales too small to observe directly. The mathematics of string theory is rich and has produced deep results, including the anti-de Sitter conformal field theory correspondence mentioned earlier. But the theory as currently formulated does not make sharp predictions for experiments at accessible energies, because the energy scales at which string effects would be clearly visible are many orders of magnitude beyond any foreseeable accelerator. Loop quantum gravity takes a different approach. Rather than postulating new fundamental objects, it quantizes space-time geometry itself. In loop quantum gravity, space is not a continuous background, but is woven from discrete quantum excitations, loops, and networks of them, from which geometry emerges at scales larger than the Planck length. The Planck length, approximately 1.6 times 10 to the negative 35 meters, is the scale at which quantum gravitational effects become important. It is 20 powers of 10 smaller than an atomic nucleus, making direct observation of Planck scale physics essentially impossible with any conceivable technology based on conventional principles. Both approaches are speculative in the sense that they have not been confirmed experimentally, but they are not speculative in the sense of being arbitrary or untestable in principle. Certain observational signatures could in principle distinguish these approaches from each other or from background-dependent theories. Lorentz invariance, the symmetry of special relativity that treats space and time on an equal footing, might be violated at the Planck scale in some theories of quantum gravity. Searches for violations of Lorentz invariance using high-energy gamma rays from distant gamma-ray bursts have placed constraints, though no violation has been found. The polarization of light from distant radio galaxies constrains birefringence, the rotation of polarization planes, which some quantum gravity models predict. The cosmic microwave background may carry imprints of quantum gravitational effects from the very early universe. These are genuine tests, in the sense that they could find violations and thereby rule out certain models. So far, no such violation has been found. The standard picture holds, but the searches continue, and the sensitivity of future instruments is expected to improve substantially. It is possible that quantum gravity leaves signatures that are in principle accessible and that future observations will detect them. The study of quantum entanglement and quantum information has itself become a major driver of fundamental physics research. Quantum error correction, developed initially for quantum computing, has found applications in the study of holography and quantum gravity. In quantum computing, error correction codes distribute information redundantly across multiple quantum bits, so that errors can be detected and corrected without measuring the encoded information directly. In holography, the encoding of bulk geometry in boundary quantum information turns out to have a structure closely analogous to quantum error correction codes. The interior of an anti-de Sitter space is encoded in the boundary field theory in a redundant way, such that the information about any local bulk region is spread non-locally across the boundary. This redundancy is exactly the property that makes it robust, and it is exactly the structure of quantum error correction codes. This connection has been developed in detail and has produced specific insights into how geometry arises from quantum information. Regions of the bulk correspond to subregions of the boundary in a specific way governed by the structure of entanglement. Local operations in the bulk correspond to non-local boundary operations. The geometry of the bulk is determined by the entanglement structure of the boundary, and perturbations to that entanglement structure correspond to perturbations of the bulk geometry. The mathematical tools of quantum information, developed for computing, have turned out to be the right tools for understanding quantum gravity. This convergence of quantum computing, quantum information, and quantum gravity is one of the most exciting developments in fundamental physics in recent decades. It is not driven by a grand unified theory, but by the discovery of mathematical structures that appear in multiple contexts and turn out to describe the same underlying physics from different perspectives. The holographic principle, the quantum error correction structure of holography, the emergence of geometry from entanglement, and the preservation of information in black holes are all facets of a single emerging picture. The picture is not yet complete, but its outlines are becoming clearer. The observation that the universe appears fine-tuned for the existence of complexity and observers is genuine and well documented. The specific values of physical constants sit within narrow ranges compatible with the existence of stable atoms, long-lived stars, and the chemical diversity that allows for complex molecules and biology. If the strong nuclear force were slightly weaker, atomic nuclei would not be stable. If it were slightly stronger, protons would fuse to form diprotons in stellar cores, and stars would burn out almost instantaneously. If the fine structure constant, which governs electromagnetic interactions, were slightly larger or smaller, the chemistry of life would be impossible. The cosmological constant, as noted, must be smaller than what naive quantum field theory predicts by 120 orders of magnitude for the universe not to have recollapsed or expanded too fast for structure to form. These coincidences are not trivial. They have been explored carefully in the scientific literature and hold up under scrutiny. Whether they require explanation through some selection mechanism, such as the anthropic principle applied to a multiverse, or whether they indicate a deeper law that fixes the constants to these specific values for reasons we do not yet understand, is an open question. The physics community is divided. Some researchers regard the anthropic reasoning as a legitimate application of conditional probability within a scientifically motivated multiverse scenario. Others regard it as an abandonment of the scientific goal of explaining observed facts from first principles. Leonard Susskind, a pioneer of string theory and one of the main proponents of the string theory landscape picture, has argued that the landscape plus eternal inflation provides a scientific framework for anthropic reasoning. The constants vary across the landscape of possible universes, and observers find themselves in universes where the constants are compatible with their existence. This is not circular reasoning on his view, but a correct application of conditional probability to a situation where the sample space includes many universes. Steven Weinberg, who won the Nobel Prize in Physics in 1979, applied this reasoning before the landscape was developed to predict the value of the cosmological constant, arriving at an estimate consistent with what was subsequently measured. This is often cited as evidence that anthropic reasoning can have genuine predictive power. Critics argue that the landscape is so vast that it can accommodate almost any observation and therefore predicts nothing. If the constants can take any value somewhere in the landscape, then any observed value is consistent with the framework. A theory that is consistent with everything predicts nothing. The debate is ongoing and has not been resolved. It may not be resolvable until a better understanding of the landscape, the mechanism populating different universes within it, and the measure problem, the question of how to assign probabilities to different configurations in an infinite multiverse, is achieved. The measure problem is particularly severe. In an infinite multiverse with infinitely many observers, the probability of any particular observation naively depends on the ratio of infinities, which is undefined without additional assumptions. Different choices of measure, different ways of regulating the infinities and defining ratios, give different predictions. Some lead to predictions that contradict observation. Others lead to the observed values. The freedom to choose the measure is a serious ambiguity that undermines the predictive power of the anthropic argument until the measure is fixed by deeper physics. These are the frontiers of current research. They are not comfortable frontiers. They involve fundamental questions about what science can explain, what counts as an explanation, and how to reason about probabilities in situations where the sample space is not clearly defined. But they are being pursued by serious researchers using precise mathematical tools, and progress is being made even if the ultimate resolution is not yet in sight. The experimental program driving this research forward operates on multiple fronts simultaneously. Gravitational wave astronomy, inaugurated by the first detection in 2015 of a signal from a binary black hole merger by the LIGO detectors, has opened an entirely new window on the universe. Gravitational waves are ripples in the curvature of space-time, produced by accelerating masses. They travel at the speed of light, carry information about their sources, and pass through matter essentially without absorption. They encode information about some of the most extreme events in the universe: merging black holes, merging neutron stars, and potentially the very early universe itself. The detection in 2017 of gravitational waves from the merger of two neutron stars, accompanied by electromagnetic radiation observed across the spectrum from radio waves to gamma rays, confirmed that neutron star mergers are the sites of heavy element production. The burst of gamma rays, kilonovae, and radioactive decay signatures detected from this event established that elements heavier than iron, including gold, platinum, and uranium, are forged in the intense neutron-rich environments of merging neutron stars. We wear gold in jewelry that was produced in the catastrophic merger of dead stars billions of years ago. Future gravitational wave detectors, including the Laser Interferometer Space Antenna, planned for launch in the early 2030s, will detect gravitational waves from supermassive black hole mergers, from the early universe, and from compact object populations across cosmic history. They will provide a new probe of the expansion history of the universe, independent of the electromagnetic observations that are currently in tension through the Hubble tension. If the Hubble tension persists through independent measurement with gravitational waves, it is a strong signal that new physics is required to explain it. The James Webb Space Telescope, launched in 2021 and producing science observations beginning in 2022, has dramatically extended our observational reach into the early universe. It observes the universe in infrared light, allowing it to detect the red-shifted light from extremely distant, extremely young galaxies. Early results revealed galaxies more massive and more structured than models predicted at very high redshift, closer in time to the Big Bang than was expected. These observations do not necessarily require new fundamental physics. They may be explained by adjustments to models of star formation and galaxy formation, but they are pushing the models to their limits and generating productive tension between theory and observation. The Square Kilometre Array, a network of radio telescopes being built in South Africa and Australia, will survey the radio sky with unprecedented sensitivity and resolution. It will map the distribution of hydrogen gas across cosmic time, trace the evolution of magnetic fields in galaxies and clusters, search for pulsars near the galactic center, where they can be used as precise clocks to test general relativity, and look for biosignatures in the radio emission from exoplanets. It represents a qualitative advance in radio astronomy that will produce a vast archive of observations relevant to fundamental physics and cosmology. These instruments will generate more data in their lifetimes than all previous astronomical observations combined. Analyzing that data requires not just larger computers, but new algorithms, new statistical methods, and new theoretical frameworks to connect observations to underlying physics. Machine learning and artificial intelligence are increasingly being applied to astronomical data analysis, pattern recognition in complex datasets, anomaly detection in large surveys, and the simulation of physical processes at scales and resolutions not previously achievable. The combination of new observational capability and new analytical tools is accelerating the pace of discovery. At the same time, laboratory experiments continue to probe fundamental physics at the most precise levels achievable. The anomalous magnetic moment of the muon, the ratio of the muon's magnetic strength to what is predicted by the standard model of particle physics, has been measured to high precision at Fermilab. As of the most recent published results, there is a discrepancy between the measured value and the theoretical prediction at a level of approximately 4 sigma, where 5 sigma is conventionally taken as the threshold for claiming a discovery. If the discrepancy grows to 5 sigma with additional data, it would be evidence of physics beyond the standard model. Candidate explanations include new particles that contribute to the muon's magnetic moment through virtual quantum processes. The precise measurement of the electron's anomalous magnetic moment, by contrast, agrees with the standard model prediction to extraordinary precision, making it the most precise agreement between theory and experiment in all of science. The difference in the muon results suggests something that specifically affects muon properties, but not electron properties, which would point toward a new particle or interaction that couples more strongly to heavier particles. Several theoretical candidates have been proposed and are being investigated both theoretically and experimentally. Neutrino physics is another area of active investigation, with potential implications for fundamental physics. Neutrinos are nearly massless particles that interact only through the weak force and gravity, making them extraordinarily difficult to detect. But they are produced in enormous quantities in stars, in supernovae, in particle accelerators, and in the early universe. The discovery that neutrinos have mass, which emerged from observations of neutrino oscillations in the 1990s and earned the Nobel Prize in 2015, was a major surprise. The standard model of particle physics originally required neutrinos to be massless, and discovering that they have mass implies physics beyond the standard model. The nature of neutrino mass, whether it arises from the same Higgs mechanism that gives mass to other particles or from a different mechanism involving a different class of particle called Majorana fermions, is not yet established. If neutrinos are Majorana fermions, they are their own antiparticles, and a process called neutrinoless double beta decay would occur at a measurable rate. Searches for this process are underway in underground laboratories around the world. A detection would be a major discovery, revealing a new class of particles and potentially explaining the matter-antimatter asymmetry of the universe. The matter-antimatter asymmetry is itself a profound mystery. The laws of physics as currently understood appear to be nearly symmetric between matter and antimatter. A small asymmetry, called charge parity violation, is observed in the decays of certain particles, but it is far too small to account for the fact that the universe contains vast amounts of matter and essentially no primordial antimatter. If equal amounts of matter and antimatter were created in the Big Bang, they should have annihilated each other completely, leaving behind only radiation. Yet here we are, composed of matter, living on a planet of matter, in a galaxy of matter. The origin of this asymmetry and the source of the additional charge parity violation that must exist beyond what has been measured is one of the major open questions in particle physics and cosmology. Experiments at particle accelerators continue to search for the source of this additional charge parity violation. The Bell 2 experiment in Japan and the LHCb experiment at CERN are both focused on measurements of charge parity asymmetries in the decays of particles containing bottom quarks, where theoretical predictions allow for larger effects than what has been observed so far. Any discrepancy between measurements and standard model predictions in these processes could point toward new sources of charge parity violation relevant to the matter-antimatter asymmetry. All of these experimental programs, gravitational wave observatories, space telescopes, radio arrays, neutrino detectors, and particle colliders, are pursuing different facets of the same fundamental question. What are the actual laws governing the physical world at the deepest level? And why does our universe have the specific character it does? Each instrument probes a different regime, a different energy scale, a different epoch of cosmic history, a different type of interaction. Together, they constitute an unprecedented observational program covering more orders of magnitude in physical scale, energy, and time than any previous generation of scientists could access. The researchers operating these instruments are not primarily motivated by philosophical questions about the nature of reality. Most are focused on specific, tractable problems within their fields. But the cumulative effect of their work is to constrain and ultimately determine what fundamental reality is like. Philosophy provides the framework for interpreting the results. Mathematics provides the language for expressing them. Experiment provides the constraint that no amount of theoretical cleverness can circumvent. Together, these three, philosophy, mathematics, and experiment, constitute the method by which science has made progress on questions that are genuinely hard and genuinely important. The questions explored in this presentation are genuinely hard. The non-reality of local realism has been experimentally confirmed. The construction of perceptual experience by the brain is well established. The holographic principle has mathematical backing in specific theoretical contexts. The emergence of space-time from quantum entanglement is a serious proposal with mathematical content. The simulation hypothesis is a coherent philosophical argument rather than mere speculation. The hard problem of consciousness is a genuine philosophical problem rather than a temporary gap in neuroscience. Each of these sits at a different stage of the progression, from conjecture to established fact. Together they draw a picture of reality that differs from everyday experience in ways both subtle and profound. The work of making sense of that picture, of developing the conceptual framework adequate to accommodate what physics and neuroscience are telling us about the nature of reality, is ongoing. It is happening in physics departments and philosophy departments and neuroscience labs. It is happening in mathematical collaborations and observational programs. It is happening wherever someone follows a question far enough that it can no longer be answered with existing tools and has the courage to build new ones. That work is where the edge of human understanding currently stands, not at a boundary beyond which there is nothing to know, but at a frontier from which the next great revision of our picture of reality will eventually emerge. When it does, it will likely look as strange from our current perspective as quantum mechanics looked to the physicists of 1890, as strange as the expanding universe looked to those who still assumed the cosmos was static and eternal. The strangeness will be the signature of genuine discovery, the mark of contact with something outside the model, with a reality that is not constrained to match our expectations.